Now for the Commodore 64. Videotape training with Commodore's foremost authority, Jim Butterfield.
Hello, I'm Jim Butterfield, and I'd like to tell you about the Commodore 64.
"14 exciting sessions on today's hottest-selling home computer. Vital, up-to-date information to inform the novice and intrigue the experienced."
Hello, my name is Jim Butterfield, and I'd like to tell you about the Commodore 64. It's a pretty good computer. It has a lot of features. Very good color, sound, picture, graphics, an excellent keyboard, a huge amount of memory, and the price is certainly right. Let's take a look inside the box and see what we have in here. The first thing you'll see when you open the box is the Commodore 64 itself. That's the whole computer. It looks just like a typewriter keyboard, but it's everything. All we need to do is to connect it up. Let's see what else we have in the box waiting for us. In here we have the Commodore 64 User's Guide. That's a very useful book. You'll need that. Don't throw it away. All sorts of cables and connectors in here. The first and most important is we need to be able to connect power into the computer. We'll do it through this transformer regulator device. But there's more. This cable is to connect from the computer almost to your TV set. In order to complete the connection to your television set, you'll need one more thing, an antenna switch box, and this comes inside the box too. It has a little switch on it. We'll show you how to use it later. Let's put the box away. And let's just take a look at the connections that you have on the Commodore 64 before we hook it up. First of all, over here we have two what are called control ports. They're used for things like joysticks, paddles, and even specialized things like light pens and so on. Next to this we have our on-off switch, but that's no good to us until we hook up the power, and the connector next to it, that's where the power goes. Let's go. We have lots more connections, so let's go around the corner here. And here we have what is called a cartridge connector. That's where most of our big things plug in, such as extra memory, large cartridge programs. Next to it, we have a little channel selector. You can select either channel 3 or channel 4, depending on which channel is available in your television viewing area. And here is the connector that will hook up to our TV set. Continuing along there, sometimes you may have something a little classier than a TV set called a monitor. If you do, you don't want this connection. That's called an RF signal. You'll want the one next to it. That's a signal for a monitor called a video signal. We'll talk about that again in a moment. Next to it, this is called the serial bus connector. This one will hook up to devices like floppy disk, like your printer, for example. Notice that one connector hooks up to everything. One connector serves all. But there's still more. The next one is where we connect our cassette tapes, our Commodore data set, as it's called now. This is a device you can use to store programs or data. We'll look at that in a moment too, but that's where it plugs in. And finally, we have what's called a user port. That can be used for anything you like, but the most common use is for a modem to plug in something for communications to other computers, to other cities. Okay, we finished our tour. Let's plug this machine in. We'll start with our power end. First of all, let's get all of these cables loose. And we'll take the rubber band off here. Okay, here we go. This is quite heavy, so put it on the floor or somewhere convenient. This part plugs into the power connector we mentioned previously. Let's take a look at that, and here we go. Okay, now this part will plug into our power plug in the floor. We'll hook that up a little later. The only thing left now is to hook up our TV set. Here we have quite a long cable. So if you have a big TV set, you can stand well back from it. There's a lot of distance here. Once again, the place we hook it up, on the back, TV sets plug into this connector here called the RF connector, and this is what goes to the TV set itself. But first, the antenna switch box. We plug it in there, and if we want to watch TV, we can hook our antenna there. If for watching TV, we switch over to our antenna. For using the computer, we switch over to computer. Either way, the signal comes in and hooks onto the back of our television set. Here, let's turn our computer around again, and we'll hook things into the back of our TV set on the little screw terminals that you always find there. Okay, and there we go. By the way, there are some sorts of television sets that have an unusual antenna connection. Instead of the two screw connections, you'll find a little, what's called a 75 ohm connection. If you have that, you can buy a little adapter at your television store to do the job on there. Now, that's all we need for our minimum computer setup. The things that come in the box and your home television set. But if you want to, you can spend extra money and you can get a more deluxe version of the 64. You can add things to it. I'd like to talk about some of those. Let's move over to the desk here and talk about what we have here. First of all, this is not a television set. This is called a monitor. About the only way you can tell the difference is that this one doesn't really have a tuner. You can't select which channel you want to watch because it isn't designed to watch television. Instead, it gets the signal directly from, on the different connector, directly from the Commodore 64, and it plugs into the video connector on the front to give you a much better quality picture. Now, this particular monitor is a Commodore 1701, and besides the regular video connector, there are some extra connections on the back which give you very, very good quality picture. If you have a Commodore 64 and this Commodore video monitor, do try to get a special cable. It doesn't come in the box. Try to get a special cable to hook up to the connections on the back of your TV set. You'll get a much, much better picture, just a marvelous picture. It's well worth the extra trouble to get the cable. Now, a monitor costs extra money because you haven't got one of them sitting around your home all the time, but it does give you a better picture, and there's another advantage, and that is you won't have to fight over who's going to watch the soap operas and who's going to use the computer at any given time. You'll both have your own hookup, and there won't be any conflict there. Let's talk about some of the other things that we connect to a Commodore 64 computer. This is called a data set. It's a type of cassette recorder, and what it contains when we open it up is a conventional cassette tape, very much like the tapes that you'd use for example, recording music. They're identical tapes, but the information on them is not music, it's programs or it's computer data. This is one of the ways of storing programs and data. A different way is to use what's called a floppy disk drive, which is this device over here. This one holds its information, once again magnetically, but on a device which is called a floppy disk. You can hold a great deal of information on a floppy disk, and you can recall it very, very quickly if you want to. But when you have a floppy disk system, you have to pay a fair amount of money for it. And so if you're economy-minded, you'll probably go over to the cassette. If, on the other hand, you want the deluxe version for storing programs, you'll probably pay extra and go for the disk. It's your choice, and in fact, you can have both. Finally, the only other accessory that we haven't talked about that we have on the table here now is the printer over here. This is used for making a permanent record of things the computer does. After all, you might get a nice report on the screen, but it's very hard to carry away at the end of the day. The screen doesn't carry around quite so easily as a piece of paper. So a printer gives you a way of recording permanently your information, listing out your programs so you can study your programs in your spare time without having to have your computer on, and generally is a very useful accessory. So that's the Commodore 64 as we'd hook it up with some of its accessories. But whether you take the basic unit or whether you add to it, you'll find it's a pretty good machine. We'll talk about it a little bit more in a few moments.
What is a Commodore 64?
I'd like to talk about using the computer, the first steps, but first of all I'd like to show you what's inside your Commodore 64. You'll never need to go in there. You don't need to give it a lube job every 1,000 miles or anything like that, but you may be curious, and just so you don't have to look in there, I'll show you what's in there in advance. Let me open it up. I've loosened up the screws already, and here goes the keyboard. We'll disconnect the keyboard connection here. That's a tough one. And here comes the pilot light. And now we can see this is the entire computer on one board. Let me show you the parts. Here we have the 6510 microprocessor. That's the part that adds and subtracts and makes decisions. It's the control center of the computer. It's the heart of everything. Over here, these chips are called ROM chips. That's where fixed memory is kept, the memory that gives a computer the style, that makes it behave in the way that it does. The big chips over here are input-output chips. They're often called interface adapter chips, and they're not terribly important to us, except you have to have input and output or you'll never be able to send your results anywhere. Along the bottom here, these little chips along here are your memory. Remember, we have 64K of RAM in a Commodore 64. And as we come, once again, back in the loop, we have two chips here which are interesting. This one is called a PLA, and without getting too technical about it, it's the traffic director for the entire computer. It hooks up the right pieces of memory to the right things at the right time. Coming over here, this is the sound interface device chip. This is the one that makes the music. And finally, inside this can, we have our video circuitry. I'd like to open this one up. Once again, you should never do this. Especially if you have a plan to play the concert piano. Okay, but inside what we'll see here is, with a little bit of heat-sealed gunk on it, is a video chip that actually makes a signal that goes to your television set or your monitor. If it goes to the television set, it goes through what's called a modulator in here. But that's really about it. The other little chips in there are just used to connect the pieces together logically. In fact, technicians often call these little chips glue because they stick the rest of the computer together. But that's all there is. There isn't very much. We'll put this one back together, and then we'll go and talk about the keyboard.
Getting started.
Before we start on the details of the keyboard, there's a couple of things on the screen when you first turn on your Commodore 64 that I'd like to discuss. First of all, you'll notice at the top of the screen there's a message that says Commodore 64 Basic V2, 64K RAM system, 38,911 basic bytes free. Now you might wonder about that. It seems that you have 64K machine, which is 64,000 bytes of memory, and yet you're being told that you have slightly less than 39,000 bytes available. Well, that's really correct. There's nothing wrong with your machine, and there's nothing missing, and you don't have to look for the parts that fell out of the box. It's all there. What happens is that BASIC itself only needs about 39,000 bytes. The extra memory is still there, but it's reserved for other uses. And you'll find that there'll be other things that you can use that memory for. 39,000 is plenty for the average program. Now, the second thing that you'll see on the screen of your computer is a flashing square. That's called a cursor, and it tells you two things. The first thing it says is the computer is waiting for you to type. And the second thing it says is when you type, that's where the character which you type will appear. And as you type, the cursor will move along to the next position so that you'll see wherever it is that the next character will go as you type it, you'll see where that will be. So it's an invitation and it's a location for you. And it's called a cursor. Now let's talk about this keyboard here. We have here that looks very much like a conventional typewriter keyboard. It has all of those letters in the center that you can never find on a typewriter and you're going to have a good time looking for on your 64 computer. At the top you have the numeric characters, similar to on most typewriters. At the bottom is a space bar, and then we have much of the punctuation gathered around it. Now, if I decide to type, I can type a number 457, or if I decide to, I can type a bunch of characters, A, S, D, F, G, H, a very popular word. Okay, and what happens is the characters, as I type them, appear as capital letters. Now, that's quite all right, but I'd like to talk about the next most important key on the keyboard, and that is over here, there's a key marked return. Now, what this key means is really do it. If I press that key, whatever I have just typed, the computer will try to do it. Now, at the moment, I haven't typed anything very sensible on the computer screen, and so if I press return, perhaps the computer might print some error message. It tries to do it and it can't do it. Or perhaps it will do something not very sensible. It's very useful to know that when we have this return key, if we don't want to do something, we just want to go to the next line, you may hold down the shift key here, and then press the return key, and that says don't do it, just go to the next line. So return says do it, shifted return says, just go to the next line, don't try to do anything that we had there. Now, there are several other important keys here, but the ones that I'd like to just mention briefly in passing is the function keys, which puzzle a lot of Commodore 64 users. They don't seem to do anything, and in fact, at the moment, they really don't do anything. They are there for your programs to recognize. When we write a program, or when we obtain a program from other places, that program will often say, press this key for this effect, press this other key for a different effect. And so what we have involved here is these keys are available for you to use. They aren't really doing anything right now. Okay, let's talk about that cursor, that flashing square on the screen. We can move it down by pressing the cursor down key. There it moved a couple of spaces, but if we hold down the key, the cursor will continue to move. We can move it to the right by pressing the cursor right key, or we can hold it down and it will continue to move. By shifting, we can move the cursor up or to the left. And finally, near the top, we have a key which will home the cursor. The key is marked to clear home. If we press it, the cursor goes to its home position, the upper left-hand part of the screen. On the other hand, if we hold down Shift and press the home key, it now becomes a clear key, and we will clear the screen. A very useful thing to do when you've got a lot of junk on the screen and you want to start over. Here we go. We have now cleared the screen on the computer. Now, at the moment, what we've been doing is we've been typing alphabetical letters on the computer. And we notice that we have a Shift key. Actually, there are two, one on the left and one on the right. And we hold down the Shift key. We're already typing capital letters, so we won't go from small letters to capitals. We're already there. When we hold down the Shift key, what we will do is we will type special graphics characters. You'll see them on the front of the key. If I press an A key, for example, holding down the Shift, I will see a little spade character. Or if I print the S key holding down the Shift, I will see a little heart character. So if you want to write a little program to play card games, there are at least two of your suits. Now, there are other graphics. In fact, there are two graphics drawn on the front of most keys. If you notice that A has a little corner on it as well as that spade key, we can get that one by pressing the Commodore key. That's the key with a little Commodore logo to the left of the Shift key. I'll hold that down and we'll press that one, and you'll see that the other graphic comes out when I press the A key. So that's a second kind of Shift key. Now, let me press the Don't Do It key by holding down Shift and Return. And now let's try something a little bit different, because there's a new feature of the screen that many people don't know about until they stumble across it by accident. If you hold down the Shift key, and while you're holding it down, tap the Commodore key, the screen changes gears, and now instead of uppercase characters and graphics, it now has lowercase characters, small letters, and uppercase characters, big letters, which means that if we want to type in text or sentences or write a letter or things like that, we now have large and small letters, upper and lowercase. So I can now say Jack and Jill went up the hill or something along that line, and put in capital letters wherever I want to. We have that capability. You notice that that wasn't there when we turned the machine on. We did that by holding down the Shift key and tapping the Commodore key. We can go back to simple uppercase and graphics by doing it again. Hold down Shift, press Commodore, and there we are back to uppercase and graphics. Okay, let's take a look at some of the specially marked fronts of this keyboard up near the numbers. There are 8 keys here from 1 to 8 which are marked with colors. Now, those are the colors that we can type on the computer. For example, at the moment, I'm typing in pale blue. Here are some X's in pale blue. We've seen that sort of thing before. Now, if I hold down the Control key, which is a new kind of Shift key, if I hold it down and I press, for example, the number 2 key, which says white on the front, here we go. Now you'll see that the cursor is blinking white instead of blinking pale blue. And the next time that I type something, those letters will appear in white. In fact, they're quite a bit brighter. I can choose many other colors if I want to. For example, there's green here, and we can type things in green, or whatever we want to. You'll see 8 colors marked on the front, and holding the Control key will give you any of those 8. But you have more than 8 colors. You actually have 16. Now, how in the world do you get the rest? Well, you get the rest by, instead of holding down the Commodore key, instead of holding down the Control key, which is up here, you hold down the Commodore key, which is down here. And then pressing the same colors will now generate, oops, let's press it correctly, new colors like gray, or, that's not a very good one, that's black, but we can choose A whole different style of colors. There's a nice gray. Oh, that's our pale blue again. We're back to it again. So we have 16 possible colors we can select simply by using these keys in either the Control or the Commodore key to select them. Now, those are the colors of the characters that we type. But there are other colors that we see appearing on the screen. For example, around the edge of the screen there is a border. At the moment it's pale blue. We can change that border to any color we want, but not by pressing a key. Instead, we must give a command to the computer. Here's our first command. We say change a certain place in memory to whatever I say, and when you change that place in memory, then the computer will change its border color. Now the place in memory is address 53280. That tells you which part of memory to use. And to change memory, use the command poke. That says change memory. Where do we change what part of memory? Address 53280. That's the place. And finally, what do we put in there? We put a comma. And then, for example, let's change the border of the screen to black. We'll type in a 0 for black. That happens to be the color code. Look it up in the book if you need it, and press return and watch the border. It will turn to black. If we'd rather see the border as white, we could type in the same command again, poke 53280, comma 1. 1 happens to be the code for white in this case. And I'd like to point out that I have put a command in the computer, and now I must say do it. How do I say that? That's the return key. I've typed in the command, do it, and there goes the border to white. Now that's one part of the screen, the border. There's another part of the screen whose color we can control, and that is the background behind the characters. Remember, we've chosen the colors of the characters individually. There are several color characters on the screen right now, but we can choose a background color. And we do that by changing a different memory location, poke 53281. Once again, these things are in the book. You just have to know that they're there so you can go looking for them. What should we change the background color to? Well, we could change it to black by selecting color code 0 again, and the background goes from blue now to black. So we can control our border, we can control our background color, and of course, we can control the individual colors that we have on the screen. Let me change the background color back to blue, because I think that's a rather nice color, 53281, comma, and that will be code 6 for blue. There we go, we're back to blue again, and now let's talk about the last couple of things on giving commands to the computer. You see, we've given a command, we typed in the command, we finished it, but it didn't do it until we pressed return. Let me show you a different command. The command print, P-R-I-N-T, says print something, and now we can put some maybe mathematical expression behind it, and the computer will do it. We'll say print 3 plus 4, and when we press return, the computer, which is do it, the computer says, I know the print command, I know what 3 and 4 is, and the computer prints 7. You can do a lot of arithmetic this way. Once again, it's in the book, but if I want to say 3 times 4, I must use the asterisk. For multiplication, we use the asterisk thing. So 3 times 4 would give us a value of 12. Now, with that sort of thing, remember typing in the command, if you make a mistake, you can back up and correct it, because until you press the return key, the computer isn't going to do it, and then you can make the command go to work for you. Now, next time we'll talk about a program. Programs are collections of commands that we can gather together in the computer's memory, and then we can say to the computer, run this whole collection of commands we have here. We'll talk about programs next time around.
Let's run programs.
You don't have to write your own programs for the Commodore 64. There are lots and lots of programs available of all sorts. There are word processors, there are business program, games, languages, and all sorts of special activities. Largely the ones that you buy come in 3 forms. First kind of form is in a ROM pack. This came, for example, Seawolf. Inside the package is a tiny little ROM pack containing extra memory inside the computer. We plug this in the back, and when we do, the computer becomes a new and different kind of machine. Let's turn the computer off for a moment, which you must do when you're plugging in a ROM pack. After all, you're connecting new circuitry into the computer. We turn it back on again, and instantly the computer has the new images from Seawolf on its screen. As you can see, It didn't take any special commands. The moment we turned it on, the computer knew it was a new machine. The machine had been almost rebuilt by plugging in the ROM pack here. Let's turn this off for a moment. It would be fun to play the game, but we want to talk about the second way that programs can come pre-packaged or pre-available for you. If you have a data set, you can get a program on cassette tape. Let's put this cassette tape program into the computer. And in this case, when we turn the computer on, the easiest way to start a cassette program running is to hold down the Shift key here and press Run Stop. Oddly enough, it should be the Shift key closest to the Run Stop. The other one doesn't seem to work so well. So we hold on Shift, we tap Run Stop, and now we see instructions on the screen. Press play on tape. Well, here's the data set tape, and we see here's a play button, so we press it, and the computer says OK, and then almost instantly the screen blanks. This doesn't mean any kind of failure on the computer. It's simply the computer has shut the screen off so that it can watch tape more carefully. In a few seconds, it will have found this program on tape. It says found roots. That's not genealogy, that's square roots. And we press the Commodore key to say, OK, go and get it. So what we have now is, by pressing the Commodore key, the program has loaded itself into the computer, and it has run. Here is a table of square roots from 1 to 20, printed on the screen. The program came from cassette tape, this one here. It's now, however, copied into the memory of the machine. I've taken the tape out. Is the program gone? No, it's still in random access memory. How can I prove it? I'll say run again. R-U-N. The program's still in memory, and when I press the return key to say, let's run it, there goes the program again. There's another table of square roots. So the program, once in memory, can be run many, many times. That's another way that you can get a program into the computer. Let's talk about a third way. Here we have some educational programs put out by Commodore, and in here we have a program which is on disk. This is a program of educational science programs. Let's plug this one into the disk drive here. We push it in this way, shiny side forward, label towards the back. We push down the little door so that it's securely in place. And now what we have to do is to, I better turn the disk on. Let me do that first of all. Turn the disk on. Now we'll plug this diskette in. And now we go over to the computer and say, bring in this program from disk. Now to do that, we must type in a command called load, L-O-A-D. That always means bring a program into memory, into random access memory, in the disk. Now we have to say which program. There are many programs on this disk, and we really should say which one. In fact, there's a little pamphlet comes along with this disk telling you what happens to be on this disk. But at the moment, if you don't know, here's a good tip for you. Instead of giving a name, just give a name of an asterisk. So I'll say load, which I've already typed, and then in quotation marks I'll type asterisk to say the first program, whatever it happens to be, and then behind that we'll say comma 8, which means from disk. When we typed it in, it looks correct on the screen, then we can press return, which is to do it, and here comes the program from disk. Now this is quite a large program. It's a fairly big educational program with animation, and so it will take a few seconds to come in. But you'll notice the difference between this and tape. First of all, the screen did not blank. Second of all, I have to give a name. I don't have to on tape because a tape might just have one program on it, or it will take the first one to come up. But the disk might have dozens of programs, and I often have to say which one. I snuck around to this time by saying the first one, but you often need to know what's on disk and which program to select. You can take it from the information that comes with disk, or in fact there's a way of asking the disk what's on this particular disk, and you'll get something called a directory or a catalog. Well, the program is now ready from disk, and that's pretty fast for a really big program. And now if we say run, what we see on the screen is the first display saying Commodore Educational Software. Press the space bar. Here we go. We'll press the space bar, and now we're going to begin a program called Boyle's Law. So this has to do with gas pressure, and we'll press the 1 key, and the computer will say, well, it draws a little picture of an amount of air trapped by a piston, okay? Give us instructions, tell us what we want to do, ask us what we want to do next. We'll press the space bar, it will ask us to set the pressure, but for the moment, we don't want to run this thing. Our Our objective here is not to learn about Boyle's law, but to learn about how we load programs. So we'll say we don't want to do that, we'd rather quit, and we'll take option 4 that says give up, and then, whoops, type it in again. There we go, I was typing too fast, and the program is over. Now, just because I've stopped the program doesn't mean it's lost from memory. Let me review again. Except for cartridges which start to run almost immediately you put them in, there are 2 steps in making a program go. First, bringing it in. That calls for a load command, L-O-A-D. And secondly, once it's in, saying run. That is a command which says, whatever has arrived in memory, do it. Do this collection of instructions called a program. Now, we've stopped the program to show Boyle's law, but we could do it again. We could say run, and since the program is still in memory, just because it's stopped doesn't mean it's gone away. If I press run and do it again, as I did with the cassette tape program, do you remember roots? The program will run again, and we'll get the same titling back. Now, apart from the programs that you can get commercially, you can also get programs in this form on disc, on cassette tape, from other sources, from clubs and from friends and from users. Many programs are generally available, are public domain. You won't have any problem getting them, but there are other sources you can go to if you want programs. For example, there are many books containing programs. If we pick up books here, we'll find that there are all sorts of programs for doing various things typed into the computer, and we could type in these program instructions and the program would run. Similarly, even the Commodore 64 User's Guide, the one that comes packed in the box, contains programs that we may type into the computer and gives us examples of how we can make certain things happen. Let's see if we can find one here. Here's a program, for example, down this one. If we type in these instructions, then, and say run, we'll have a program in our computer. In fact, we have plenty of books of this sort, and we also have many magazines. Some are published monthly, some not quite so often, which contain many, many programs of various things. All of these magazines are published with plenty of programs, and we can take these various magazines, put in the programs, and eventually we'll have a running program by typing these in. Now, one thing I'd like to point out to you, however, is these programs are pretty big. If you take a program like this one, for example, which is for the 64, it starts on this page and then continues through all of these pages through. You can see that's a lot of typing. Now, it's probably a very good game program, so you'll probably have quite a good time playing the game once you've typed it all in. But typing in that huge amount of material means a couple of problems. First of all, a lot of rather careful work. And secondly, possibly a couple of mistakes that you'll have to look for and correct if the program doesn't run correctly. Now, that's okay. It's a good game. You spend a lot of time. You type it in. You run it. You say, what a wonderful game. But if you shut the computer off, the program's gone. There's nothing left. And the next time you turn your computer on, the next day or the next week or whatever, and you want to do that program again, guess what? You'd have to type it all in again. Well, you don't have to. There's a way, once you have typed or entered a program into the computer, and once it's ready and running reasonably well, you can then copy it onto cassette tape or onto floppy disk and then bring the program back anytime you want to. We call that copying save. In other words, we can tell the computer once a program is ready, save that program onto cassette tape, save that program onto floppy disk, and the program will be there, and then we won't have to type it in the next time. We can just call it up from where we have placed it in storage. Now, there's one other way you can get a program, apart from buying it, getting it on disc or tape, or typing it in from a magazine, and that is you can write a program yourself. But to do that, we'll have to talk a little more about what a program really is. And we'll do that next time.
What makes programs work?
In order to use a computer effectively, it's useful to know how a program works. That's what we'll talk about here. You may recall that previously we looked at entering in direct commands into the computer. For example, I could say print 33 plus 44, and the computer would reply 77. That's called a direct command, we could put exactly the same type of command into a program, in which case we would call it a statement, and it would be stored and used later, not used right away. So here's what we might do. In order to store a command, we put a number in front of it. I might put a number here, 100, and then behind it, the same command, print 33 plus 44. And when I press return, the computer, instead of performing the command, will store it away. And then we can use it at a later time. The command, we didn't print the answer now. The instruction is stored. Now, if you want to enter a program, you have to be careful, first of all, that any old programs you have in there are disposed of. You don't want them sitting around. You want to start with an absolutely fresh computer, so you say wipe out the old programs by typing in the word new, N-E-W. Now we're ready to type in the instructions of our own program. We're using a simple language which is called BASIC. BASIC has simple commands such as print, input. We've seen some of them before. You'll find many of them in the Commodore 65 User's Guide. Now, let's take a look at why we would store commands. Why don't we just type the commands in and get the work done right away? Well, it turns out that when you gather commands together into the computer's memory as a program, some brand new things start happening that you don't get with direct commands. These basic statements can work together in a brand new way. There are, of course, always the commands that do things, the commands that print, the commands that calculate, and so on. But there are some new kinds of commands. For example, there's one set of commands that's good for creating repetition, so we can do something over and over again. Here's the idea. Once we've stored a command into the computer's memory, we can do it as many times as we want. Hundreds of times, we don't have to put it in again. If we can only bring in repetition, what some people call looping, because the program goes back and repeats again, then we can use that program statement over and over again and save a lot of work. Second thing that we have here is the ability to use some instructions and not use others. Let me give you an example. Suppose that we're printing out a large number of customer bills, and we have written into our program to say, print on the bill, your bill is now overdue, please pay promptly. Now, we don't want to use that communication every time. There are some communications, there are some customers who will have their bills up to date, and you don't want to print that message. So here's what we need in the computer. We need decision. We can decide, yes, we'll perform this activity, or no, we'll skip over it and go on to the next part. So here are the three parts. First of all, the action part, the part that does things. Second of all, the repetition part, the part that goes back and does the same thing for the next customer or the next item of information. And thirdly, the decision part, saying, in some cases, perform this piece of these set of instructions. In other cases, don't. Skip them. Now, with all of those, we can have the flexibility we need in our computer. Now, there's one more thing that's useful to know when we're talking about how a computer handles information, and that is variables. Suppose we have some calculation we want to do, but when we write the program, we won't know what the numbers are. We won't know what the sales results are until they come in, and we're writing the program beforehand. We won't know the customer's name because the customer might not walk in until a month after we finish writing the program. So what we have to do in the program is we have to leave blanks in the program and say, we'll fill these blanks in later. And we can tell the program to work on these blanks and make all of this stuff work at the time. Now, these blanks are called variables. In BASIC, anything that we give a name to is a variable. For example, I can say x equals 123, and when I press return to say, do that calculation, the variable called x will be stored somewhere in the computer's memory, and it will hold a value of 123. But any time later, we can say to the computer, print x, and the computer will look in its memory, find the variable or the blank we have filled in called x, and print its value 123. In fact, we can do more than that. We could say print x plus 100, and when the computer goes into its memory, it will print 223. It fetched the value of x and then performed the rest of the arithmetic. These variables, these things to be filled in later, are very important. If we didn't have them, the computer would always have to calculate on the same numbers every time. But there's more than numbers. There are also names. We can store names and addresses and codes and anything we want to in a non-numeric fashion. We call this kind of thing a string variable. Let me show you one. If I say X with a $sign behind it, what I mean is this is not a conventional variable for use in arithmetic. It's not a number. Instead, we have a name. Okay, let's take a look. We say X string equals, well, we can put in a name, Jim Butterfield. And once again, when I press return, the computer will say, okay, I'm now holding a filled-in blank area called X string, and filled into that space is a name, Jim Butterfield. Now, these things work together. With the blanks that we can fill in, called variables, and with the control features that we have, the repetition and the decision, we can write a program to do almost anything. In a moment, we'll talk about how we can fill programs into the computer.
Putting programs to work.
If you want to enter programs into the computer, either because you write them yourself or because you read them from a magazine or book, then there's a few things that would be useful for you to know. As you know, you're going to put in your program lines starting with a line number. That's a number ahead of the line which says, don't do this now, save it, and we'll do it later. For example, we could say a given statement here, and we could type it in, and when we press return, that would be the end of it. Now, what happens if you make a mistake? Well, the easiest thing, if you haven't pressed return, if a line isn't in yet, then you can use the delete key and go back, and you won't have to worry about the mistake. It will never have been entered into the computer. Okay, now we can finish this line, and when it's finished, then we press return. Now the line's in the computer, and if we have a mistake on it now, there are several things we can do. First of all, if you see anything wrong with a line that you've typed in, all you have to do is to type the line in again, correct it. If I put it in again, the moment I press return, the old line is removed and the new line that I've typed in will replace it. It recognizes that that's a line to be replaced because it carries the same number. The old line 100 is gone, the new one is there. In a moment we'll talk about what happens if you miss out a line, but here's something that's very useful. Since you often forget to put a couple of things at the beginning of your program, it's usually fairly good to start with a moderately high line number like 100. And since you may omit things that you need to do within your program, you should skip the numbers along, perhaps 10 at a time, starting at 100, going through 110, and so on. Let's type some more material in here. We'll type. Okay. Now, somewhere along this line we say, okay, we've typed in a program line, we've made a mistake, there's something the matter with it. Another thing we can do rather than typing over is we can go back and we can type in a correction right on the screen. And even though we haven't typed in the whole line, pressing return enters the whole line all over again. So that when we make a mistake, we can correct it right on the screen without having to type the entire line. This is called screen editing. It's a very useful feature of the thing. So we'll enter some more lines, and I will say print. Okay, we've entered several lines into our program. At any time, we can look at what we have entered by saying list, L-I-S-T, and we'll see a list of the lines we've put in. Remember, before you start, you should say new to clear the computer of any old lines that are in there. Now, if I decide I want to insert a line that I've missed in between, say, a couple of lines that are already on there, all I have to do is to pick a line number that's in between. To put a line between 110 and 115, for example, 110 and 120, I'll enter a line 115. And the new line will take its place and the old lines will move over to make room. One last thing, if for some reason you have a line of coding in there which is wrong, or you simply want to take out entirely, you can remove any line by typing in its line number and typing nothing behind it, just return. So if we don't want line 120, we type in 120 and then press return, and that line is gone. Once again, at any time, we can list. Now, if this is our final program, there are several things that we can do. If the program is ready now, this is not a very big one, we can say run, and the program will run. That's a pretty short program and doesn't do anything terribly exciting. If we'd like to take away a copy of our program for study, and we have a printer, we can transfer a listing of that program to the printer. How to do it is in the book and in the printer guide. It's a rather curious series of statements where we have to first of all make a connection to the printer, and then we say, let's divert all of the things that would normally go to the screen, we'll divert them over to the printer instead. And now we're ready, we'll say list, and instead of listing to the screen, the computer will list to the printer. Here we go. And there's our program on the printer. We can tear it off, take it away, study it, and decide what we want to do next. If you ever do this, you should terminate this procedure with a print number 4 that disconnects the printer. Now, as well as doing that, once we have this program ready, we'll probably want to keep it so that the next time around, we don't have to type it in again. Here's how we do it. On cassette tape, we say the word save. By itself, that would be enough. But we can do more. We can give it a name. I'll call this program Hi There, so we'll say save, in quotation marks, Hi There, and the moment that I press return, I get the instruction press record and play on the tape. The cassette tape is already inside the machine, so I'll press record and play, and the screen blanks, which is what always happens when we're reading or writing tape. In a few moments, this is a fairly short program, so in 15 seconds or so, the tape will stop and the screen will return to us, and then we'll talk about doing exactly the same thing when we save this thing onto disk. Okay, the program is saved. I'll simply stop the cassette tape here, and now we'll take a disk, place it in a disk file, and we'll do exactly the same thing, making a copy of this program to disk. We type in almost the same command. This time we must have a name. Everything going onto disk must have a name because we can save so many things on disk. And so we say save Hi There, but we also have to say one more thing, comma 8. 8 is the device number of the disk. When we want to save to the disk, we say save program name, comma 8, and out it goes. I'll press return. The disk will start to spin. The light will come on. The program is being written, and now the process is complete. It was a lot faster than on cassette tape, but of course that's one of the things that you get when you buy a floppy disk. Next time we'll talk about how programs can store data on disk or tape for you. This is storing data. We've seen how to store programs. Now we'll take a look at the next step.
Storing information.
This time I'd like to talk about how we store data so that we can use it later. We'll normally store it on floppy disk or cassette tape. There's an interesting difference between programs stored on disk and tape and data stored the same way. Programs tend to remain about the same. Once you've written a program, it shouldn't need changing unless you find there's a mistake in it or there's some change in your practice in doing whatever it is that you're doing and you need to keep a new kind of information. But your data files will be changing all the time as customers come and go, as they pay their accounts, as they charge new things, or as you add to your record library, or whatever you're keeping track of, your data files will be changing all the time. That's what they're there for, okay? But they can be kept in exactly the same way as we keep programs on this sort of stuff. Now, I'd like to talk about the general setup of information stored on there. It's not just a formless mass of information. It's arranged in a certain way. If you looked inside a filing cabinet, you could probably pull out one of those filing folders and you would call what you had there a file, and that's what we call these things on the computer. Collections of information are called files, but they do have a certain structure. If you open up your filing folders, you would see a number of sheets, each dealing with a certain sort of thing. It might deal with a student, it might deal with a customer, it might deal with a sale, it might deal with a book in your library. And what we call those is we say, well, I have a record on this book and I going to put a record in here about this new book that I just bought. We call these items of information about a certain thing records. And that's exactly what we call them on the computer. Each file contains a number of records, information about things. Within each record we have a lot of detail. Some of the detail is constant, some of it changes. We have, for example, a person's name, a person's age, their customer balance, whatever it is, and so on. And some of these fields are relatively constant. They hardly ever change. For example, a customer's name doesn't change much. Customer's age doesn't change until they start getting past 50. Then the birth date starts moving back a little bit, or moving up a little bit. But in any case, we have fairly fixed information, and then we also have variable information. As they purchase things, as they pay their accounts, some of these other fields change quite rapidly. Each of these fields then come together to make up a record, a unit of information on certain things. We may have a lot of records in the database or only a few. I suppose if you set up a file on the LPs that you have in your stereo system, then you'd call these things about records. But whatever they are, you'll have one for each one of the items you're logging. They come together to make a file. Now, there's one more level. If you have a collection of files that work together, for example, you have a group of sales transactions, excuse me, you have a bunch of sales transactions which are on one particular file, and on a different file you have customer names and addresses. When you want to process those, you might be bringing in the sales transactions here and bringing in the customer names and addresses and making them work together to print bills or whatever you're trying to put together. Now, when files work together, we usually call that arrangement a database. We'll be talking here about sequential files. And we'll be putting some of these into our computer. We can put those onto disk, we can put those onto tape, and we'll do a simple example of that sort of thing. But one thing I'd like to point out, first of all, is that we write programs, we type them in on the machine, but we don't write files. Programs arrange to write this information on disk or tape, and we give the information to programs. So we write programs, and programs write files. That's generally how it works. Now let's take a look at a type of file called a sequential file. That's one thing stored behind the other. We can see that's the way it has to happen on cassette tape, because the tape reels along, and if you want to put record number 50 in there, it will have to fit behind record number 49. The same is often true of disk. We have sequential files on disk. That means if we want to search for a certain record, we'll have to wade through all of the ones which are in front. That's usually no problem. The computer's pretty fast, and it'll find the record you want without too much trouble. There is a special kind of file available for disk called a relative file. It's somewhat more powerful, but it's somewhat less common. We won't talk about it here in a moment. And by the way, a relative file is not a collection of your cousins and uncles that live in other cities. Let's talk about how we write a file here. I have a program in here which is about to write a file, and I'd like to show you. It's going to write the file on this cassette tape that we have here. We'll close the door so the tape is ready to go. I'll say run for the program, and now the program says, are we ready to start tape? Yes, we are, because the tape's ready to go. And so we'll say yes. This is a program that wants us to give it 5 names. It will write 5 names for our bowling league on there. It says press record and play on tape. Yes, we have to do that ourselves. There we go. The screen blanks as it usually does when there's tape activity going. And in a few moments, after the header is written, this is written with the name of the file and says, hey, what's coming behind this point will be a data file. In a moment, the screen comes back and the program continues, and it says enter 5 names. Well, I suppose we can say the first name will be Bob, and the next one will be Carol, the next one might be Ted, the next one might be Alice, and the last name might be Leroy. But the interesting thing here is that while I've been typing in these names, the cassette tape hasn't moved. What happened? I'm typing all of these names, they're being sent to the file, and yet we don't hear them on here. Well, what happens is this, that the information isn't written on tape as it's generated, it's collected, and only when you have a certain block of information to make it worth writing tape will you do that. The information is held in a storage area in the computer called a buffer in this case. Now, when I write the last name, then the tape will start to move, and so I'll press return. Name number 5 is in there, and the tape is now moving. You'll notice the screen has blanked once again, and in a few moments the data will be completed. It will be written on tape, and now it's on our file. Let's stop the tape. Let's rewind it and take it out for the moment. That data is written here now. Even if I turn off my computer, we can bring it back from that magnetic tape anytime we want to. Okay? It's relatively permanent. Now, let's see if we can read it back in. The computer program said we'd like to rewind it and play back, and I'll say, sure, I want to do that. It says now press play on tape, not play and record. And now it will take a little time. First of all, the cassette tape has to look for the program header. Remember, we wrote a header with the name of that data file on it. And after that, it will then go for the block that contains the data, bring it back, and print it on the screen. Okay, we've just finished going by the header. In another 7 or 8 seconds or so, we will have our data back from that cassette tape. And here it is, Bob Carroll, Ted Allison, Leroy. We have stored it on tape. We have brought it back successfully. Once again, we'll stop and rewind the tape. Okay, what have we found out from that? Well, that we can write information quite successfully to a cassette tape. We can do almost exactly the same thing to disk. This is a data file. It is no longer a program file, but it writes in approximately the same way. We should keep very closely in mind what we have going here in terms of the structure of a file. In this case, we have only one field inside the record, just a name, and that's each record. This could be our bowling team. If, for example, Ted decided to opt out, we could replace that name and write a new file and so on, because files are made to be changed as are needed. That's enough about file for the moment. Next thing I'd like to talk about is a Commodore 64 used as a tool for education and learning.
The Commodore 64 as a learning tool.
Computers are often good in a classroom environment. Certainly there's a lot of excitement in education. Students seem to like computers. Very often the most common thing we see computers used for is drill and practice. The computer puts a question to the student answers the question, then another question gets placed, and so on. If the student gives an incorrect answer, perhaps the correct answer will be shown. This sort of thing is called computer-assisted instruction, which is abbreviated CAI. Now, there are some people in education who feel that the students should not be forced into too narrow a channel, and that the computer has many more uses than pure drill and practice. They like to talk about the general environment where a computer can help any learning process, whether as a supportive device, whether in simulations, whether in even game-like situations. That's usually called by a slightly different name, computer-assisted learning, or CAL. Whichever way you go, the teacher in the classroom now finds himself or herself in a rather strange position. First of all, you have great enthusiasm, great energy on the part of their students. But the teachers themselves feel that it's perhaps difficult for them to learn to be expert programmers in order to deal with the material that they want to teach. What can they do? Should teachers become programmers? Should programmers become teachers? It's not an easy question to answer. The average classroom teacher does have a few things to do. The teacher can buy teaching programs, buy software which can be used in the classroom if suitable material can be found. The teacher can even challenge students to prepare the material and try, let's have a contest and say whoever can write the best teaching program gets a prize. They get to write another one. Something useful like that. You'd be surprised at what a reward that can be for students. And finally, there are some attempts to make teaching or preparing teaching materials on a computer easier. There are specialized languages such as Pilot in which you really don't know how to program. All you have to know is how to go about preparing the material, plug it in, and Pilot will organize the presentation for the students. It's not really programming, it's organizing material. But perhaps, once again, Pilot often causes teachers to force their information into too tight a channel. Now, we'll talk about games and simulations and other things that are very good in the learning environment in a moment. But what I'd like to talk about now is that it's probably always best if a student has a large range of options. If a student is simply being forced to put in simple canned replies, there's less interest in there, and perhaps there's less excitement. Perhaps we're throwing away some of the good things the students bring. Let me see if I can show you a simple drill program which is organized so that it allows the student to exercise certain options as desired. This is a simple example of an addition program. We'll say run, and the program says this is a simple addition 4 plus 7. Now here we're using the 4 function keys on the right-hand side of the computer. At the bottom of the screen they're identified. The function 1 is called a help key. If you don't know the answer, you press that key. The question here is 4 plus 7. If we press the F1 key, the answer 11 will appear on the screen, and now a new program is set in there. Anytime we want to try our hand at doing it, 8 plus 6, well, perhaps that's 14. We can type in the answer, and we're identified, yes, it's correct. 7 and 3, we'll try 9. No, that's wrong. And the border of the screen changes color for the moment so we can see visibly that something's happening here. We could also have sound to give us an audible signal that something is wrong here. Now, that's one of the things that we can do. We can ask the computer for the answer anytime we're still trying to learn. We still really don't know how to do this sort of thing. Eventually, we can try filling in these things, and when we get enough right answer, we may say, hey, we're ready for a test. When we enter the test mode, which is the key F7 down here, then we're going to be marked on what we put in. Now, the point that's being emphasized here is that the student doesn't have a single path. If the student doesn't want to answer, he or she doesn't have to. The student can simply say help and get the correct answer. This is the area where they are. When the student thinks he or she is ready, then we can press key F7 and go from exercise mode into the test. There are 10 questions. If we answer them correctly, we'll be marked, and the teacher will be able to see. 6 plus 5 is 11. That one is correct. Now we're at test number 2. 7 plus 7 is 14. That's also correct. If at any time, however, the student feels that maybe it's not time yet, the test is premature, we can always go back, and we can always do more exercises and take the test again later. That's the kind of interaction that's probably good. And this is a very simple one, that the student is in control. The student can say, I want to do more practice, I want to do less. I'm ready to qualify myself and say, hey, I'm ready. But the more options we give people, the more creative a person feels on that kind of machine. And very often, creativity is what it's all about. That's all I want to say about the general principles of computer-assisted instructions. Next time, we'll discuss computers talking to computers.
Computers talking to computers.
A computer seems to be an isolated little device. But in fact, by adding equipment, you can make your computer talk to the world. There are some technical problems to be solved here. Mostly you'll want your computer to communicate over telephone lines. And telephone lines were designed for speech. Computers that want to talk to other computers can't use speech. Even if they could talk, the computer at the other end would have trouble listening to speech. Instead, we have to convert the bits that are inside the computer into frequencies that can be passed over the telephone line, and then we have to change the frequencies from the telephone line back into the bits that the computer at the other end will accept. Changing the bits in a computer to frequencies is called modulation, and a device that does that is called a modulator. Now, when we get to the other end, the frequencies have to be changed back to bits, and that's called demodulation. We do it with a demodulator. And then communication is a two-way street, so at either end we have a modulator sending the signal, and for the other path coming back to you, there's a demodulator doing the whole thing. This results in a machine which does both. It's both a modulator and a demodulator, and so we call it by the rather peculiar combination name of modem. We need one of those. Here, for example, is a commercial modem. This one plugs into the communications interface on the back of the computer. We can plug it in back here at the rear of our Commodore 64. But that's not quite enough. The telephone line, by the way, plugs in to the little hole over here, okay? But that isn't enough to do the job. This is just a piece of hardware, and it doesn't know how to get the bits on the line. It'll ship them there when we deliver it, but in order to make the modem work, we have to have a program to go with it. And if you buy a modem for communications purposes, you should make sure that you also get a compatible program to help you talk to computers at the other end. Let's talk a little bit about what goes over the telephone. We know that it's frequencies so that the telephone can be used in its normal manner. But there's something else going on. A special code is used for communication, not quite the same as the code that's inside the machine. It's called ASCII, A-S-C-I-I, which stands for the American Standard Code for Information Interchange. And it's a good thing because even different makes of computers can talk to each other that way. Now let's assume that you've connected up a modem and you're ready to talk to the world. Who are you going to talk to? Well, there are several different places. Let's try to itemize it. First of all, in many towns and communities, there are computer bulletin boards. There are computers that will receive your call, accept the messages from you, store them away, and deliver these messages to other people who called in. It's a little bit like a bulletin board in your home. You can hang up notices saying, for sale, one computer going cheap, or whatever your particular communication happens to be, and other people will read that and perhaps answer you. You'll have to call in again to get the answer. What kind of a price do you pay to use a bulletin board? They're usually free. They're usually done by individuals in your community or neighborhood. In the evening, when they're not using their computer for anything else, they hook it onto their telephone line and use it that way. What else can you use a computer for in the communications world? Well, you can call into databases, large computers that handle a great deal of information. There are many commercial databases around, such as, for example, The Source, CompuServe, and several others. They not only store information, but they are, in and of themselves, very large computers, and they can also do large-scale computing, in case you find something that Commodore 64 is a little too small for or a little too slow for. So you can tap the resources of bigger computers, and you can tap their information too, perhaps stock reports, perhaps other things. Here we have a computer that we've used for several things. For example, we contacted CompuServe, and on there we have the CBM Club. That's on Commodore business machines, and it tells you news and information from Commodore on the new products and things that have been happening. You might have new information on the 64 from there. What else can we do? Well, over on the printer, we have the Shop at Home feature. We can actually look around and look at products that we can obtain. It's a little bit like a mail order catalog. Another thing, we have on the screen right now, we've interrogated the computer and said, what flights do you have going from Denver, Colorado to London, England? Well, it turns out that the computer has searched its memory and looked for all of the connections, and what we have here are, for example, one direct flight that takes place at about 8:15 p.m., and we have two flights involving connection. One of them, it looks like it goes through Boston, and the other one goes through Denver. I'm sorry, through Salt Lake City. We started at Denver, didn't we? That's the way we can sort out information. It can be right up to the minute. It can be very, very informative. If you want to evaluate your stocks, if you want to read perhaps the latest sports information, if you want to be trained on something, learn something, you can do that. Because when you put a communications port on your computer is no longer alone. When you go to use your computer, you can share information with the entire world. And that's a very good thing to be able to do.
Commodore 64 language.
Many people are confused by computer languages. You don't need to be. Computer languages are just the ways that we write programs for the computer. And in fact, as a beginner, you'll use the languages that come with a machine. We'll talk about other languages later, but first I'd like to make an important distinction. Computer languages themselves are the commands that you use to write a program that will work for you. But there's another part of the computer that's related to a computer language that we often don't think of, and that's called a computer operating system, sometimes a computer monitor. And what that does is that one is the part of the computer that lets you talk to the computer, that makes the connection between all the pieces. When I type on that keyboard and the results appear on the screen, that's not happening automatically. That's a computer operating system doing it for us. Now, we usually assume that that's there, but the difficulty is this, that one of these days you may switch over to a rather different kind of monitor or operating system, and then it comes as a shock if you don't realize that the computer, the way it speaks to you and the way you speak to it, is part of a programming system, and it can be changed. Now, we'll talk a bit about the computer languages that come in the machine. We've seen BASIC already, and we'll be taking more looks at BASIC in the future. BASIC is a nice, simple language. BASIC stands for Beginner's All-Purpose Symbolic Instruction Code, and it's quite an easy language for beginners to gain their first familiarity with a computer. Very likely you'll be dealing in BASIC because it's there. When you turn the machine on, it says 38,000 and change bytes, BASIC bytes, free. It's part of the system. So this one comes with a system, but there's something important I'd like to mention about BASIC in a moment. It can be changed. BASIC comes in a ROM chip, a read-only memory chip, and you think perhaps it's frozen forever, carved in stone, written in silicon, if you like. But in fact, it's possible to flip that chip away and to put in its place a different version of BASIC, or for that matter, any other language you choose. We'll come back to that in a moment, but I'd like to mention something else. There's another built-in language in this computer. It's the one that really does all the work. It's called machine language, and it's how the machine itself works. Now, the visible thing about machine language is that because it's right inside the circuitry of the machine, it runs very, very quickly. It's fast. Probably that's the cosmetic part of machine language. The important part of machine language is that once you get into it, you get a better understanding of the insides of the machine, because everything works by machine language making it happen. Even BASIC is machine language doing all the work for the BASIC language. I'd like to demonstrate to you just a little bit of machine language so that you can appreciate its dazzling speed. If I go over to the computer now, which seems to have a blank screen, I can touch keys, and by touching a key, suddenly the screen fills with characters. So accordingly, if I touch more keys, we can get a different set of characters appearing in the various parts of the screen. Now, machine language is fast. BASIC couldn't possibly fill the screen with characters like that. Okay? We can see that we have something working here that's many times, maybe dozens of times faster than BASIC. Let's talk a little bit more about machine language. We certainly aren't going to show you how to program it now. It's not fundamentally difficult, but the thing that you have to keep in mind about machine language, it's a new sort of discipline, and it's a little more mechanical than the BASIC we use. It's not quite as helpful to us. But for the moment, let's switch into a communication device called the Machine Language Monitor. And here we see a series of hieroglyphics, and now we're no longer talking to BASIC. This is what we call the operating system or monitor. We're talking to the insides of the machine. If I want to display memory, I don't say peek anymore. If I want to print something, I don't say print anymore. I must know the communications language that I have to use here. I suddenly have lost all of my usual BASIC communications. I'll do a simple memory display. That happens to be our program, but unless you've had quite a bit of practice, you're really going to have a lot of trouble reading it. Doesn't matter. We'll return back to BASIC. BASIC says ready, and this looks much more familiar. Remember, machine language is in there. If you see the machine doing something with dazzling speed, it's probably the built-in machine language doing it. Now, I'd like to show you something rather different. This is BASIC, and of course, if I type print 100 plus 22, it prints the answer 122. That's a BASIC that we've grown to know a little bit. It's not difficult. But as I said before, you can make your own BASIC. Without having to bring in anything from the outside, without having to plug anything into the back of the machine, we can flip the old BASIC away and bring in a different BASIC. I've prepared a very slightly different version of BASIC in the machine, and if I flip away the standard BASIC, my BASIC, which is already stored in this machine, will come to the fore. Let me change that with a simple poke. I'm going to type poke 1,54, but don't you do this unless you also have prepared a BASIC in memory, because otherwise the regular BASIC goes away and you don't have any language left. I'll say poke 154, the new BASIC is working, and one of the few things that I've done to this machine is to say, instead of saying ready, say hello. So this BASIC, I can say print, as before, 100 plus 22, and it will do so, but when it's finished it says hello instead of ready. A very small difference. I've had one other. If I put in a line that means nonsense, we know that the standard machine says syntax error for something that makes no sense at all. I've gone into BASIC and I've changed that message, and so my BASIC says something slightly different. When I press return, it says idiot error. Now, these are small and cosmetic changes, but you do have the capability of making major changes to the BASIC language if you want to. You're not fixed with any single kind of BASIC or any single kind of language. And in fact, if you have something in the computer like a word processor or other large thing, you don't need BASIC at all. You can move it right out and use that memory space for whatever else you'd like to use it for. We'll talk in a moment about the extra languages that can be added to the computer. We've talked about the languages that are built into your Commodore 64 microcomputer. But there are languages that you can also add to the microcomputer that are not built in already. I'd like to talk about a few of them. First of all, I'd like to talk about something that is really not a computer language. It's an operating system. That's CPM. It stands for Control Program Microprocessor. And it's an operating system that is, it's not a language to write programs in. It's a way to communicate with a computer to make it work. Quite different from the one that you've seen before. Now, let's take a look at a CPM system. We have one built into the computer here now. It's similar to programming systems used on other large microprocessor computers, and therefore there may be programs you can buy which fit on these other computers that will also work on the Commodore CPM system. It's a transferability of program type of system. There's a lot of computers which use CPM. Let's take a look at what we have here. Now we have a CPM system. There's quite a different message on the screen. It says Commodore 64 44K CPM system. And it has 2 copyright statements on it, but the interesting thing is you can tell it's not BASIC because it doesn't say ready. Instead, what it prints is a capital letter A followed by a greater than sign that looks a bit like an arrow. And what you'd find is that all of the communications we've learned for BASIC don't work on this system. In other words, if I say print or catalog or save, none of them work because CPM has its own language and its own way of doing things. For example, if I want to see what's on the disk, I might say dir for directory. That's what I have to type in, dir, not catalog. I'm doing this, and now a CPM directory, which looks quite a bit different from a BASIC directory, is appearing on the screen. We won't go through any of these programs or indicate what they do at the moment, but the sort of thing that's interesting here is that when we want a program, we often don't say load. The program will come in, but we have to just give its name. For example, there's a program in there to help look for bugs, look for errors in programming. It's called Dynamic Debugging Tool. And because it's there to get rid of bugs, we abbreviate it. What else? DDT. To bring it in, all we do is type its name, DDT, press return, and the program starts to come in here. It will take a few moments for the program to come in, but when it does, we'll find once again we're still working in something of a foreign language with the computer. DDT it doesn't work like regular programs, and we'll find that the screen doesn't behave like regular programs. It's in now. If I want to look at the registers in the computer, I can type X and return, and we get a printout that's showing us there. But it's not our purpose here to show in detail how to use CP/M, simply that we have a totally different line of communications from computer into the system when we have a different operating system like CP/M in place. Let's take DDT out with using a Control-C command, which is quite standard in CP/M. CP/M operating system itself will come back in, and the system will take over. Again, let me emphasize, you don't have BASIC. If you want BASIC, you'd have to bring one in from disk. There might be several BASICs you can get with CP/M. You might bring in other languages and not BASIC. Pilot or Logo or Pascal or COBOL or Fortran. There's plenty of them. But in they come, and now we're back to CP/M, and we once again have our A and greater than sign, the prompt saying CP/M wants our next command. Now let's not continue with CP/M. It's rather a specialized field, but instead I'd like to show you what makes up CP/M. This is a rather big box that we plug into the computer to make CP/M work. In fact, it's this big because it contains an entire computer system of its own. There's an extra processor in here to make CP/M do the things that it does. That's why it's rather large, rather complex, but that, of course, is the key to its compatibility. CP/M has the same processor chip as many other computers, and therefore it will work the same. Okay, that's probably all we need to say about operating systems at the moment. Let's talk about a few other computer languages. Logo is a language which has been getting a good deal of attention in education. The most visible part of Logo is that it's a turtle language, which can be explained this way. It's as if we have a little controllable device rolling around on the screen, and when we say go forward 10 paces, it moves that distance. When we say turn right, it turns right, and so on. This is often used for younger children in the school environment to learn the rules of logic. Logo is a very interesting language, but let's do a couple of simple turtle things first. We'll say forward 50. And as soon as we do so, and as soon as I press return, the turtle will appear. It will move forward 50. There it is. You can see it's moved up. The turtle is a little white triangle near the top. Now I'll say, well, let's turn right, let's say 135. And we can see that it's turned around. Now if I say forward 50, again, we can see that the turtle has now moved through an angle. Now with these sort of commands, move forward, turn left, turn right, move a certain distance, we can do some very pretty things on the screen. In particular, if we want to, we can build pre-written routines to do certain things. For example, if I say to the computer, whoops, if I must spell it correctly, however, triangle, the computer will draw a triangle on the spot. It will move forward the right distance, turn to the right angle, and do several other things. The definition of a triangle is involved in this case with the definition of a number of angles, but we can see that definition if we want to, but the important thing is that if we have something called triangle, we can call it several times. Let me call triangle. And there's a triangle. Let me call it again. The turtle has moved slightly. If I call it again, it will draw a triangle in a slightly offset position. And again, triangle. And you can see we're starting to build a sort of pattern. This is the sort of thing that can be very enriching for younger children. They can work around with various sort of diagrams. We'll complete this triangle, which I think we call a star. And here we go, drawing a series of triangles so they come together like a fan, a wheel, or a sort of very highly multi-pointed star. There it is. We could also draw other figures. For example, we have one composed of a number of circles. If we say circle, there is a circle being drawn from the turtle starting point. If we want to draw a series of circles, we could ask for, say, a flower, which is a series of there goes the first circle. The turtle will shift and draw another one, and you can see that something which is rather flower-like is being drawn on the screen. Now these are all very nice, but what's the point of it? Well, first of all, it teaches children the ideas behind logic. The whole idea behind describing a flower in what we might call a subroutine of the computer, and they're just calling it up by saying its name, teaches something about building logic and building it in a module. It's there to be used. And then we can build many flowers. We might build a flower bed by calling the command flower many times in different situations. It's, in a way, a logic trainer. There are other Turtle programs, such as, for example, the Turtle graphics package turned out by HES. Logo is particularly an interesting language in that it's based on a much older language called Lisp. Lisp stands for List Processing Language, and it's a language of how things interrelate. Lisp is traditionally the language of artificial intelligence. That's a whole story in itself. But what we really have here is a very sound language with some very interesting trimmings on it, mostly used in education. Let's just talk for a moment about some of the other languages that you can get for the Commodore 64. We can get some through CP/M, as we mentioned before, and there are also languages such as Pascal, which is a very formalized computer language, Pilot, which is an authoring language for educators, as we've mentioned before. We've talked about Logo. There's a new language from Denmark called Commodore, which combines the ease of BASIC with the power of a language like Pascal. And there are many, many others. Why would you pick another language beside BASIC? Largely because you have a certain job to do, and other languages are better suited for the job that you're after. For most of us beginners, the thing that we need to know is that BASIC comes with it. BASIC's probably a good way to start. There's always that powerful thing called machine language on the inside. But finally, if you find that BASIC, for some reason, doesn't measure up to a certain job you have, there are other languages available. You can take BASIC out, you can plug the new languages in.
Graphics.
Graphics is a very interesting characteristic of the Commodore 64. You've seen some of the fine graphics that can be done with games. What I'd like to talk about now is the techniques that are used to make graphics happen. Mostly they're used in programs. You won't need to do that unless you try your hand at programming. But it's interesting to know how some of these things are accomplished, and some of them are easier than you think. Let's talk about the first kind of graphic, and that is you can draw pictures using ordinary characters, letters of the alphabet, numbers, and all of the special symbols that we find on the front keys there. I'd like to show a simple example of that. Here, if I press a key, I can cause a face to be drawn. That face is two letter O's, a letter V, and an equal sign. And we can draw a border around that face if we use the special graphics which exist inside the Commodore. We're just using the special things that are built in. All these characters are built in, and you can draw some quite fine pictures using the ones that are there. But you can do it a better way if you need more detail, if you need things that aren't available in the existing graphics. Easiest way of doing it is this. You can change the existing characters, A, B, C, D, E, E, F, and the special graphics and so on, into a special character set of your own. I've programmed the computer so that now some of the alphabetic characters have been changed. Let's go and take a look at them. I've changed the letter A. In fact, I've changed this partly to the Greek alphabet. The letter A is now the Greek alpha character. There it is. Okay? The letter B is the Greek beta. And as you might suspect, the letter C has been changed to the character called gamma, and the letter D to a delta. We could have changed out the characters to the entire Greek set or any other set you want. If you want to write in Hebrew or Cyrillic or Arabic, define your own characters. The 64 has the capability right within its software to do all of that. But we can do other things. For example, I defined another letter here into a rather curious character. Doesn't look like anything, looks like a bit of code. Let's take a look at that and say, why would we do that? Well, perhaps you might be able to guess if I show you a different character that I've defined. Now, I've swapped out parts of the alphabet for this one too, but here's what we have. If I put all of these characters together, this one, and then this one, and then I'll go down to the next line and put down this one and this one. What do we have? A smile face. Fairly large with a bit of detail on it because it's 4 characters put together. Now, when I finish, and if you see the principles here, I'd like to ask the computer to return to its normal alphabetic characters, and you'll see these things displayed on the screen return to their normal alphabet. And you'll see which keys that I pressed to make it happen. Here we go, and there are the characters that I was really pressing to make those things happen. So, principle number 1, use the built-in characters. Principle number 2, if the built-in ones aren't good enough, build your own. Principle number 3 is a whole different thing. The 64 has a remarkable feature called sprites. Now, a sprite is almost like something that has a life of its own on the screen. It moves around independently and can be controlled independently of everything else. And so it may pass in front of something, and the material it passes in front of will reappear. Let me show you a couple of simple sprites like this. We can see a couple of balloons moving around on the screen. And you can see, in fact, that the yellow balloon is moving behind the alphabetic characters, and the white balloon is moving ahead of them. We can make this sort of thing happen. I'll stop these sprites for a moment and show you another feature. I'll simply stop the program. The thing about sprites is that they are so independent on the screen that they seem to have completely a life of their own. It's almost as if somebody pasted them on top of the screen and they have nothing to do. I'll list part of the program that we've been running to do these characters, and you can see the sprites simply aren't affected by that. They stay on the screen all by themselves. Let's continue this program. I haven't finished yet. The sprites will continue moving. Okay, and you can see that they move around among the characters and don't really have any problems there. And then we'll go back, and I want to look at one other feature. Now, we've talked about then the regular characters and graphics, building your own, adding sprites, and you can do all of these. And then there's finally one more thing. You can use a truly high resolution to manipulate any part of the screen you want. The smallest thing you can draw on the screen is called a pixel, P-I-X-E-L. And a pixel is a very small thing. You can get hundreds of them across the screen and hundreds vertically. So a pixel is a very small dot on the screen. Now, if we can individually turn on and off any pixel and perhaps choose its color to a limited extent, then we can draw some very detailed things. Pixels can be used for example, drawing mathematical curves. They can be used for sketching using a light pen or a graphics tablet, and they can give you a great deal of control. Let's take a look at a simple math curve drawn using pixels. You can see that that logarithmic curve that we have on there is outlined by turning on individual dots on the screen. That's pretty good. That's pretty impressive. That's probably the hardest way to do things, although it's not really hard. But the important thing for you to know is you have a lot of options. You have some very rich graphics available on the Commodore 64.
Commodore 64 working for you.
Here's a letter, and I see from my notes that everywhere I say VIC-20, I should have said Commodore 64. Let me call up that feature and say, I want to change and replace every place that says VIC-20 to Commodore 64. It says more. No, that's all I want to do, and let's simply do it. And here we go. And you can see the letter is now changed. The 3 occurrences, it's all changed. What else do I need to do? Well, I say I've missed out a word. Right after the word disk, I'd like to insert the word printer. Let me go into insert mode, and what you'll see is that when I type in that word, all of the rest of the paragraph moves over to make room. P-R-I-N-T-E-R. See how easy it is? Another thing that I decided, there's a sentence down here I'd like to move earlier in the whole operation. So here's what I'll do. I'll select a sentence operation here and say, I can pick out the characters one by one here, just a moment. Here we go. You can see that I'm picking out part of the text and selecting it. It's coming in an opposite font, But I can say, give me the whole sentence. There it is, and a couple more letters. And that's the part that I want. Now, what do I want to do with it? I want to move it up here. Okay, so what do? I say, use the move command, and here goes that sentence. It's moved up to the new place. You see it there? Now, I'd better take it out of the old place. It's still there. I've just made a copy. So I'll use the other command, and look down below. You'll see the sentence that I had disappearing from the screen. There it goes. It's pretty handy. It's a very nice way to rewrite a letter. Is there anything else I need to do? I could move in the margins, I suppose, somewhere up near the top. I see this questions plural, and I want questions singular. I'll take off the S. Let me just find the right place here. There's the letter S. I'll simply delete it. And that looks pretty good. I'm ready to type the final draft of my letter. Here I go. Whoops. Not that way down. Let me erase that. Like that. And now we'll do it again. And here comes my letter. I'll stop the letter now because we don't want to see the whole thing print, but let's talk about some of the things that I've done. I've used a word processor. The document that I composed is saved onto disk. I can bring it back into the computer's memory, change it, change around complete words and phrases, substitute one word for the other. Mr. Smith could become Mr. Jones, for example. I can compose a letter and I can make it very, very good. And when I'm finished, it'll come out word perfectly. This is called word processing, and even now we're only showing a little bit of its potential. The particular one that I'm showing here is called paperclip, but there are many, many word processors that you can get commercially. It's up to you to choose the one that has the style that you want. For example, we have here many of them. There's Hesswriter 64, EasyScript, Quick Brown Fox, and there are others that I still don't have here, for example, such as WordPro and many others. There's quite a range of prices, quite a range of features. What you have to do is to choose the one you want.
Commodore 64 Music.
There's some good music can be played by the Commodore 64. It has a built-in chip which is called a Sound Interface Device, the SID. I think Commodore planned to call it the Sound Interface Chip until they thought of how it abbreviated. Then they decided on Sound Interface Device. Now it does a lot of good things, and you've heard some of the sound effects and music played during the games. I'd like to show you how some of that happens. We won't talk about the special sound effects. Those can be done by any old chip. I'd like to talk about music. That's where some of the quality of the SID chip really comes out. The first thing that we should talk about in music to understand the waveforms, to understand how it works, is waveforms. That's the basic sound that any instrument produces. It might be mellow, it might be sharp, it might be thin, it might be brassy, but every instrument has a certain waveform. Now, I've set up the computer so that it will play the next few notes rather like an organ. That is, when I hold down a key, it will play the note. When I let go, it will stop immediately. And so what we're going to do is concentrate on the waveforms we can hear. The first waveform I have here is a triangular waveform. That's soft and mellow. It's the sort of sound you might hear from a flute. Let's listen to the triangular waveform and hear its mellow sound. Pretty good. Pretty soft, right? Not all instruments sound that mellow, however. Sometimes we want a little edge on them. Sometimes we'd like to have a bit more harmonics, as musicians call it. In that case, we might choose another waveform called a sawtooth waveform. Now, a sawtooth waveform, as you might suggest from the name, has a bit of an edge on the sound. It's much sharper, and in some ways, it's much richer. Let's listen to a sawtooth. Sounds quite different, doesn't it? And yet that really isn't the whole combination of waveforms that we can use for instruments. There are several others in there too. Sometimes instruments have a rather thin and perhaps reedy sound to them. That's called a pulse waveform. There's more than one kind of pulse waveform. I'll play the thin one first. We'll call that a pulse wave, and you'll hear what it sounds like. It's a little thin. It's a little sharp. Listen. Okay? No mistaking that, and yet sometimes we want it. Finally, the last kind of pulse wave is a particular type called a square wave. That sounds rather rich and full and perhaps a bit brassy. It sounds a little bit like the sawtooth, but not quite the same. Let's listen to a square wave waveform. Okay, that's pretty good stuff. Now, we've listened to the basic waveform, except for noise, which is used for drums and gunshots and things like that. But now let's talk about something else. Apart from the basic kind of thing that the instrument sounds like, its basic waveform, there are other things that give the instrument its characteristic sound. And that's how quickly the sound starts and how the sound stops. We use the terms ADSR, which stands for attack, decay, sustain, release, to describe how the sound starts, holds, and stops when an instrument is played. In fact, we call this the waveform's envelope, but we don't have to use this term. If we know what attack, decay, sustain, release is, we'll be okay. Let's talk about those. Attack is how quickly the sound appears. If you have a percussion instrument, something that you hit or strike or pluck, the sound will start right away. Then we have decay. That's how quickly the sound fades out after it's first struck or begun. Some instruments don't hold the sound for more than a moment. Some hold it for quite a while before it settles down. For example, if you hit a piano key, you may notice that at the moment that you strike that piano key, it's a little louder than the sound that settles down a moment later. That's the decay part. Now some instruments will sustain and some won't. Here's what we mean by sustain. On a piano, if you hold the key down, the note continues to sound. But on a guitar, or say a bass guitar, after you strike it, the sound will fade away. There's nothing you can do. Same thing is true, say, of a xylophone. Once you hit that note, it has to fade away. The only thing you can do is hit it again. And so we can't sustain some instruments, but others we can. For example, if we want to, we can hold down a piano key, and the sound will sustain. If we want to, we can continue to blow into a trumpet or a mouth organ, and the sound will keep going as long as we don't run out of breath. And so these instruments have sustain levels, and we can state how long they will stay in there. And finally, we have release. And that's how long it takes the sound to go away after you let go of the key. You may have noticed that when you let go of a piano key, it still sounds for a moment afterwards. When you stop blowing into a trumpet, there's usually a little bit of sound left over. Let's use some of those principles on the waveforms we've already listened to and make certain kinds of instruments. For example, our first waveform is chime-like. We'll use a soft, mellow, triangular wave, and we'll make it start immediately. When you hit a chime, it starts to sound right away. But then we'll give the sound a long time to die away. We'll give it a long decay and release. Here we go. Listen to the mellow chimes. Okay? Recognize that mellow triangular wave in there? And yet we've changed it completely by adding an attack and a fadeaway cycle to the whole thing. Now sometimes we want to do exactly the same kind of envelope, attack very quickly and fade away rather slowly, but we don't want that mellow waveform. If we struck a guitar, the waveform would be much sharper. A guitar has a sharper sound. Let's take the sawtooth wave, the one with an edge, and let's play that through exactly the same attack, sustain, decay, release envelope and see what we have. Here's a guitar. Listen to the difference. Now that sounds pretty good. Perhaps sometimes on some struck instrument we don't want to hold it quite as long as we've shown here. For example, a banjo. The sound doesn't hold as it does in a guitar. It fades away rather quickly. And so perhaps we could once again change to the rather thinner sound that a banjo would give us, and say, and let's have a fairly fast release, a fairly fast decay on this one. Let's listen to how the sound would change. We're going to the pulse waveform and listening to a fairly fast attack and a fairly fast decay and release. Here we go. Once again, it's different. The envelope makes quite a difference. Finally, all of the things we've talked about so far have been fast attack, instruments that we strike, percussive things, things that start to sound right away. Other instruments take time for the sound to build up. For example, a trumpet, a mouth organ, or even when we're bowing a violin, it takes time for the vibrations to reach full strength. On those, we want a slower attack and perhaps a medium sort of sustain to hold the level as long as we want to. Let's listen to the difference. I've set up a square wave for the bold, brassy sound of a trumpet, and I've set a moderately slow attack. Listen to how the sound comes in, and a moderately fast decay. Listen to it fade away. Here's a trumpet. Do you hear the difference? That's the way that we can put forth the basic waveform, which gives us our music quality, soft or rich or mellow, together with our envelope, which tells us how quickly the sound appears and disappears, to give ourselves a real musical thing. Now, we've been playing 3 notes, but we've been playing them all with the same instrumentation. Let's play a little tune here. Okay, let's play a little tune here which uses 3 different instruments, a bell-like or chime-like instrument to carry the melody, something sounding more like a mouth organ to carry the second piece, and down on the bass there's probably a big bass guitar or something that sounds like that. Let's listen to a little music here. I've been asked by the television taping staff not to dance along with the music, so I think I'll have to sit this one out.
Computer games and simulations.
Games are a lot of fun. Sometimes I think the word game is stuck on almost everything that isn't serious. If you play music, if you draw pictures with a computer, that's not a game. You don't get a score, but we call it games. And there's sometimes this down thing. Don't play games. Don't play around on the computer. And yet there's a lot of good can come from game playing. I was just playing UMI's Motor Mania, which comes on a cassette tape here. And that one is a rather nice game for hand-eye coordination. I suspect it doesn't teach rules of the road terribly well, but all games have a purpose, and I'd like to talk about that more in a moment. Games, of course, come on cassette tape, as I've shown. There are games which are on disc. Here's Space Rescue. We'll look at that in a moment. And, of course, games. The quickest way to get a game into the machine is to plug it in on a cartridge on the back of the computer. Let's take a look at some more games. They show off the computer very, very well, and it's often the best way to assess a computer's graphics and sound features. I'll load Space Rescue into the computer.
We knew exactly when to come on every time.
So Space Rescue is sometimes called Benji. You can see the little dog in here, which is going to help you on your voyage of discovery. Now, the rather interesting thing about this game is it has a high educational content. It also has a lot of rules. You'll need the little book to go with it if you want to do it. Let's go and take a look at the objective of the game by indicating in our joystick what we want to see. Space Rescue. We'll pick a rank for Benji. We'll make that fairly low for an easy game. A lot of instructions here, but let's get straight to the game. Now, we're ready to play. And the first thing that we know is that we're supposed to look around and look for lost scientists and bring them back to Earth, and that's okay. But I'd like you to look at the educational content of this game. Let's take a look here. I'm going over to take a look at details on the various planets. For example, if I call up details on Earth, here's a great deal of quite accurate statistics on the planet Earth. Let's go back And let's look for details on, for example, the planet Saturn. And here's the known information on that planet. In other words, you can play the game. You can also learn quite a bit about what's going on within these within the solar system, for example. Okay, we'll very simply do a little bit of traveling around among the planets, looking for our scientists, but we certainly won't play this game through. Let's go back and let's say to the engine room. Okay, here's an engine room report, and we would like to go to, why don't we go to Jupiter? And here we go. And let's do it. Off we go. We're on our way to Jupiter. Now, at this point we have control of our craft. Down we go to the surface looking for our scientists. I'm afraid things are getting very busy on Jupiter, and we really don't want to show all of the interesting things that can happen on this particular exploration. What I'd like to point out, however, is that much of this kind of game and many other games are based on a good deal of useful information. You play the game, and whether you know it or not, you're learning a great deal more about the world around you. Now, beyond games, there's a closely related kind of program which is called a simulation, which actually attempts to imitate something, perhaps a solar system, perhaps a microcomputer chip, and those can be very useful in education and for other things. I'd like to turn to another program, and I'd like to show you the COCO program, which simulates the inside of a microprocessor. Let's take the COCO program, also by HES, and let's put it into our computer. I'd like to show you some of the parts here. Once again, an instruction book. We're simulating a large fictional computer. This is an interesting thing. This plugs into the joystick part. It's part of a security connection, sometimes called a dongle, and that will make sure that you're an authorized user of this package. Let's plug it in where the joystick goes, and very soon we'll be ready to load in the COCO program. Here we go. COCO is a program which simulates the internal workings of a microprocessor. What we have are the internal registers that we could never see in an ordinary microprocessor. Now, what we see on the screen is a group of mythical registers, real registers in this mythical microcomputer. Down towards the center, we have our three information registers, A, X, and R, they're called in this case. On either side, we have memory, which is called H and L for high and low. We have 5 locations in each. Over to the right, we have a score, which tells us how efficient our program is. Our I/O, which means our input-output area, what's coming in and going out. The next command that we'll execute. And finally, the status indicator telling us what we're doing at the moment. Along the top, we have the commands that we may enter. We're going to tell the machine to run in just a moment. And across the top also we have the messages that may turn out if we do something wrong. Along the bottom is our program, and we'll ask the program to run now and see how the internal workings of the computer can be demonstrated and animated on the screen. Let's take a look at these instructions. We can see that a value is being moved into the A register. That's the first instruction. And so on. The various instructions will be performed as they go. Now, this isn't a real microcomputer we're seeing, but some of the principles can be shown in here and some of the internal architecture. And so we have a simulation activity, which is also a challenge to the students. After they go through example programs, they might be asked, here, try your hand at making a program that will do this in the COCO microcomputer. So we can see a simulation can do something that we couldn't do in real life. You can't really look inside a microchip and see the registers in there. Now, that's probably the thing about games. It's a challenge. And make no mistake about it, it's a mental challenge. So what we have going here is a game's a great motivator. You want to write something, even in education, to make people want to play, to be challenged, think about how the games do it. Then you'll learn a little bit more how to use a computer effectively.
Now what?
We've had a chance to see some of the things you can do with a Commodore 64 computer. It's only really been a quick run through, but perhaps some of the potential of the machine is there. Don't let the technical stuff frighten you. It's only there to make everything work. Don't feel you have to be a programmer. You don't, although sometimes programming can be most of the fun. Why else would somebody stay up until 3 o'clock in the morning cursing and then claim the next day that they had a wonderful time? That's part of what it's about. I hope that one of the things we've communicated with you is the 64 is not only a versatile and a useful machine, good for business, good for home use, but also it's a great deal of fun. And more than that, it's a challenge. Because today that's probably the biggest turn-on, to know that you can test yourself against a computer and make things work and make things go. I hope you've enjoyed the little time that we spent together. Stay with it. You're only really beginning to appreciate the things that you can do on this machine. Above all, the computer's there to have a good time with. Enjoy it.